Hi, my name is Sonika Tyagi. I'm going to give you an introduction to NGS data quality control. I must acknowledge that this material has been put together by Platforms Australia training platform, and several trainers have been working on developing this material in collaboration with ABI. So I'm going to cover the following topics. What does the raw data look like? Specifically talking about the FASTQ format, what common types of errors and contamination you may expect in sequence data, and what is the impact of those errors and how to deal with those. So before introducing the NGS sequence format, I wanted to just remind everyone of FASTA format, where you have a sequence identifier and starting with a greater than sign and usually some unique sequence identifier from the database, and then from the second line onwards you have actual sequence. And when you have multiple of those sequences in the same file, this is called a multi-FASTA file. And similarly, with the NGS platforms, what we have is a new sequence format. It's called FASTQ format. So it's similar to FASTA format, but there's also an additional information, which is the quality. So in FASTQ format, you have, again, a sequence identifier line. And here it starts with an @ sign. And this line has a lot of information about the instrument where this sequence was generated. So it will have instrument ID, the flow cell ID, and coordinates of that flow cell, like which lane and what tile number, and also the X and Y coordinate of that read, and also the index that was used to identify that read. Second line contains the actual read sequence in the form of ATGC, and where the letters could not be identified as one of the 4 nucleotides, you have an N there. And then third line is generally an empty line that starts with a plus sign, and it's just an optional space in the format to store any additional information. The fourth line is the quality string. So in this line, you have these different characters, and each character represents some quality that corresponds to the base pair at that position. So each base has a quality, typically ranges between 0 and 40, and current instruments go even above 40 these days, and this scale is called Fred quality score. And if you wanted to correspond these quality values to accuracy, so from 10 through to 50, the accuracy increases from 90% to 99.999%. And quality is calculated as a negative log of probability of a base being called incorrectly. So just coming back to this quality string again, this quality, these characters are represented by printable characters on your keyboard, and these are also known as ASCII characters. So all these characters have been used by different sequencing platforms to represent quality. So these characters in computer language also have their own what we call decimal value that computer recognizes, and for quality string they represent a quality value ranging between 0 and 40. So for example, this exclamation character has a decimal value of 33, and it represents quality of 0 in one of the scales. And similarly, there's another character here this has a decimal value of 64. And why these two values are important is that we have quality scales that represent a value of zero quality score by exclamation sign, and in some other platforms the value of 0 is represented by this this @ sign, which has a decimal value of 64. So Originally, the Sanger sequencing follows a Fred plus 33 offset um, um, scoring scale. So it used all the values ranging from this character up to I to represent different quality scores. But when Illumina launched their first sequencing platform called Celexa, they decided to use Fred 64 as their starting value. So this will represent quality score of 0, and they also use some negative values in their scoring scheme. And in the subsequent release, what they did is that they got rid of these negative values. So they used this range of characters to represent quality in their FASTQ files. And subsequently, they changed this again a little bit and had a different scale that they were using in this particular version of their sequencing uh, formats. But the good news is that all of the current Illumina data has gone back to following the original Sanger scale. Okay, I don't know the reason why they kept changing this scale, but I think now it's all back to the original Sanger scale, and it's just to be should be aware of that there have been different quality scales that have existed, just in case you're using some old data generated through one of these platforms. Yes, so just the same thing represented here, like you have different scales that are that follow different scoring scheme. Now, why it is important to know um, which of the Illumina platform your data is coming from is because of these overlapping reasons. Because for these two scales, these letters represent high quality data, whereas for these three intermediate scales that were used by Illumina for some of their sequencing versions, these same set of characters will be representing the lowest quality. So it's just good to be aware of that. And some of the tools can give you an option to specifically telling the software which scoring scale to expect, and other software may be smart enough to just decipher this information by themselves. Yeah, same thing what I just said. Fred 33 encoded good characters may be Fred 64 encoded bad quality characters. Okay, so yeah, I've just stated that yeah, with most of the software, you'll be able to explicitly state if which scoring scale was used, and it's a good practice to use that option. Now, what are the different reasons of the various errors that you see? So it goes from less common to most common type of errors. So sometimes you have entirely bad reads, and that may be because of something went wrong with the instrument, and in some cases you would see duplicate reads, that the reads are or generated from the same region of the genome or transcriptome. Sometimes you may have adapter running into the actual DNA fragments. You may have indels or bases that were not recognized at one of the nucleotides, and you'll have N in place of that. And most common type of errors that we see in Illumina data are of substitution errors. And typical error profile will be you will have bases that are miscalled, and normally quality starts to go down towards the 3' end of the read. You may also have genuine contamination in the data because of just during handling of the samples, you may have some actual biological contamination, and sometimes you may have PCR primers and adapters going into your actual DNA fragment sequencing. So just good to be aware of those, and when we do data cleaning, we look for all these common type of errors that we expect in the data. When I say adapter contamination, adapter can be like just partially embedded into your read or completely within the read. So there are all these different kind of combinations are possible, and particular adapter finder will look for all these possibilities and remove adapters from your actual sequence read. And why do you want to clean up the data? Because if you have errors in the data, some of the bioinformatics workflow are going to be affected. You may miss out on an actual, like a genuine alignment because of errors in the reads. And this becomes very important when you're looking for variants, because a sequence error may be confused with a SNP and vice versa. And especially in case of de novo assembly, we rely on overlap at the ends of the reads. And because of errors, you may miss out on actual overlap between the reads. And errors may also cause the software to run slowly, and it may require more memory and may produce incorrect results. So how do we deal with with all these errors? So by now we know what are the typical errors that you expect in a particular NGS platform, and then you can look for those errors. And if you find there are evidence of those errors in your data, you can try and remove those. One of the tools that is commonly used to look at the overall quality of the NGS data is Fast QC, and it gives you various matrices. One of the metrics is a box plot of the quality scores. You have quality scores on the y-axis and read length on the x-axis, and it's also color coded. As I told you, the quality scores starts from lowest to highest here. So anything below quality score of 20 is not considered very good quality, and then between 20 and let's say 28 is okay quality, and anything above 28 is really great quality. So the plot is also color coded, and in this particular example you can see most of our bases are in this green region, so it represents good quality data, as opposed to this sequence data where you have lots of bases dropping below quality value of 20. There are ways how you can clean up the data. We will learn about quality trimming. So you can do quality trimming, retrimming in two ways. That you just fix the position. For example, in this case, we'll just remove all of the bases after position, let's say 21, and you will remove all of these bases from your data, and you will be left with this read length of 20. The other criteria could be that you just use quality value, and you say only if at the end of the read you have bases below quality value of 20, only remove those. So you'll have reads of variable lengths that will be left with after you clean up the data, but in that case you'll recover more data than fixed trimming. But in some of the software you may have to do fixed trimming, because that may be a requirement for a software that all of the reads should be of the same length. And there are other ways to remove low quality bases. One of them is sliding window, and we will also look at how to look for adapter sequences in your data and how to remove those. We will use Fast QC to assess the quality, and I will use a tool called Skewer to do the trimming. There are a number of tools that exist for looking at the quality of the data and how to clean up the data. And there are the different properties of those tools that you can look at, and depending on your requirement, you can pick one over the other. So in conclusion, QC is critical for downstream data analysis. A range of tools exist to visualize and deal with poor quality and data contamination. And if you are stressing about throwing away the data, you haven't done enough sequencing. So you always account for errors in the data, because none of the sequencing platforms are 100% foolproof. So always expect to throw away some data, and but do look at quality of the data before you start any analysis. Thank you.